NCERT questions of P block, boron and carbon is what we are going to talk about in this session today. This is Shishir Mittal from Vyas Edification, and block chemistry presents a very interesting perspective of the entire inorganic chemistry. As a matter of fact, boron is at the heart of entire P block. So, let's begin. Discuss the pattern of variation of oxidation states of boron to thallium, and there's a B part also. Carbon to lead, boron to thallium and carbon to lead. What is the variation in oxidation state? This has been asked. We are supposed to mention that and discuss that. Let's discuss. If you just write down the important points, you would notice boron, aluminium, gallium, indium and thallium. Now, oxidation state typically of boron, typically the oxidation state of boron is +3, +3, +3, +1 and +3, +1 and +3. Boron also shows a rare state of -3, which is not shown by others. Why? Because boron is a non-metal, while aluminium to thallium are metals, and metals never show oxidation state which is negative. So, -3 of boron is visible only because boron happens to be a non-metal. This is one variation. Everybody is showing +3. Why are they showing +3? They are showing +3 because they have 3 electrons in outermost orbit, ns2 np1. This is the general configuration of group 13, and since these 3 electrons can be lost, they all show a common oxidation number of +3. However, as you move down, you notice that indium also begins to show a state of +1. Although +3 is more stable for indium, still it does show +1. And in case of thallium, it is +1 which becomes more stable as compared to +3. Wow, why? There is a very unique thing called as inert pair effect. It so happens that 6s2, 6p1, now 6s2 electrons in thallium become somewhat inert and they are no longer interested in formation of bonds. Is it a similar trend in carbon to lead? Let's take a look. When you talk about carbon, Kartik, Shri Ganesh, Shankar Parvati. There's a shortcut to remember the family, the entire Shiva family you can say. Carbon, it does show +4, +4, +4. We have +2 and +4. We have +2 and +4. Carbon actually shows a number of different states also. Like silicon could be, carbon being an organic, the source of organic chemistry, carbon can show all the oxidation states from +4 to -4. So carbon is a very unique element in that sense. Silicon and germanium are metalloids. Along with +4, they also show -4. Tin and lead are metals. Because they are metals, they never show -4. However, they are capable of showing +2 state in addition to +4. In case of tin, +4 is more stable than +2. And in case of lead again, +2 becomes more stable than +4. Some answers are very similar. General electronic configuration is ns2, np2. When both the s and p electrons are lost, 4 electrons are lost, and that is why a common oxidation state of +4. As you move down, the stability of lower oxidation state increases. So, carbon, silicon and germanium, for silicon and germanium, +2 is so unstable that it does not even exist. Tin, +2 begins to show up, although +4 is more stable. Only in the case of lead, that is 6 period, you have 6s2, 6p2 is the electronic configuration. You find that 6p2 is lost easily. 6s becomes inert. It is relatively more stable. Okay, wow, that's very interesting. Yes, that is very interesting. Now, you find that, I repeat, carbon does show rare other states also from +4 to -4, actually carbon can show multiple fractional states also because of millions of organic compounds which carbon can make. But again, these are the trends. Now, can we explain the trends and anomalies? Inert pair effect, yes, it does remain. I'll talk about that. But other than that, metals do not show negative states. Metalloids and non-metals can show negative. That is why -4 for them. And carbon has a special status. It can show various different states. Why? Because it forms millions of compounds in form of organic compounds. Due to catenation property, it forms a large variety of compounds. And because of that, carbon can show really numerous oxidation states. So we have explained 3-4 points. Negative states of boron, carbon, silicon and germanium, that is one trend. Fractional states of carbon, that is the second thing. Third thing is indium and thallium, tin and lead, they start showing lower oxidation states also due to inert pair effect. And only in sixth period you find that the lower oxidation state actually becomes more stable than the higher state. Why? We say that in each case 6s2 electron has become inert. Why do we say it has inert pair effect? Can we explain inert pair effect also? Yes. What we can say is this: down the group, size increases. 6s is a huge orbital. It's large in size, and because it is large in size, electrons don't repel as much, and they are reasonably happy because they are spread over larger volume. They are more stable. Not just that. Number one, electrons are more stable on their own. Plus, if you involve them in bonding, if you involve them in hybridization, what you find is this. This is ground state. And excited state is this. Just watch. You make one electron jump and you get excited state. And then this excited state undergoes hybridization 1, 2, 3, 4. Then you have sp3 hybridization, and then you find 4 bonds being formed. This is typically in group 14. I'm talking about group 14. Similarly, you can talk about group 13 also. You just take just one electron off, excitation, and then you can have sp2 hybridization in group 13. Now, this excitation involves some increase in energy. From 6s, if the electrons have to be excited to 6p, you have to give some energy. What is the advantage? The advantage is instead of 2 bonds, now you can form 4 bonds. Down the group, bond length increases, yes. Because bond length increases, bond strength decreases, yes. If the bond strength is less, and if that extra, you are forming extra 2 bonds in this case. In case you show excitation, you get 2 more bonds to form. Usually what happens is with higher up ones, carbon, silicon, germanium or boron, aluminum, gallium, more number of bonds means more energy is released. This is profitable business. Down the group, size increases. Bigger size means longer bonds means weaker bonds. The bond strength decreases. So, moving down the group, bond strength has decreased. Yes. At the same time, excitation becomes more difficult because 6s electrons are very happy. They don't want to get excited to 6p. So, excitation keeps on becoming more difficult, and after excitation you can form new bonds, but new bonds are no longer as profitable. So, you find that lead and thallium in 6th period do not discover sufficient motivation or profit in this excitation and forming 2 extra bonds. In excitation, you have to give energy. In 2 bonds, you get more extra energy released. Investment is more and release is less. They don't like it. And that is why you have the so-called inert pair effect in which 6s2 electrons don't much like to participate in bonding. And that, my dear, is the reason why the stability of lower oxidation state increases on moving down p block. I have mentioned this in reasonably good details. We have mentioned 3-4 points. Number 1, why common oxidation state of +3 and +4? 1 point I have told. Second point, why negative states for a few? Third point, why fractional for carbon? And fourth point, the inert pair effect statement. Fifth, also the logic or the reason of inert pair effect also we have mentioned here. And I hope this is very useful to you. In case you want a very regular answer, this is the answer. You can take a screenshot. But then what I have told you verbally is a much superior answer. Can you explain the higher stability of BCl3 as compared to TLCl3? Yes, we can. Why? Watch. BCl3 is predominantly covalent, right? So you have one boron happily joined with 3 Cl atoms. It is beautiful, it is lovely, it is a non-metal chloride, and it is what it is. It's fine. In case of TLCl3, TLCl3 is somewhat ionic. So it involves Tl3 plus ions and 3 chloride ions. Now the problem actually lies with Tl3 plus cation. Why? Thallium has electronic configuration xenon 4f14, 5d10, 6s2, 6p2. It is like this, right? Now out of this you find, sorry, 6p1. Thallium would be 6p1, right? Out of this one electron can be easily lost. If it is lost, I get thallus ions. Very nice. But the moment you want thallium 3+ would mean that 6s2 electrons also have to be lost. 6s, now s subshell, please understand, s subshell is more closely attached to nucleus as compared to p subshell, number 1, in general. P more than D, D more than F, but S is held most tightly by the nucleus. It is more difficult to lose 6s electrons. Also, on moving down the group, the size of orbital increases. Bigger orbitals means larger volume. If electrons are spread over larger volume, they are more stable. If they are more stable, it is more difficult to lose them. So primarily what you find is, on moving down the group, you find that the reactivity of this electron pair becomes very, very poor. And this is called inert pair effect. And this is called inert pair effect. So what is inert pair effect? Poor reactivity or the lesser tendency of reaction for 6s2 electrons, or in general ns2 electrons, on moving down p block is called inert pair effect. And due to inert pair effect, thallium plus 3 is not very stable. It has a tendency to react and come back to thallium plus 1. And that, my dear, is the reason why thallium plus 3 is not very stable. And boron being at the top is very comfortable with oxidation state of plus 3. So it manages to stay that way. That is the reason. Why does boron trifluoride behave as a Lewis acid? Well, you have BF3. Let us draw the Lewis dot structure of BF3. This is the Lewis dot structure of BF3. And you would notice, if you count the number of valence electrons of boron is 3 into 2, which is 6. Why 3 into 2? There are 3 bonds and each bond contains 2 electrons. So it has 6 valence electrons, but the octet is incomplete. So in order to complete an octet of electrons in its outermost orbit, boron would love to accept 2 electrons if anyone happens to give an offer. And what happens, say, in case if there is any other species, like say if you have another F minus ion. This one says, okay, I'm donating 1 electron. Boron says, yes, please, I'll accept. And boron accepts. And what do you get? You get B, F, 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 F. You get BF4 minus. What is this? Once you get BF4 minus, yes, my dear, this is what we say. And in this case, F minus is lone pair donor and BF3 is a lone pair acceptor. And the species which accepts a lone pair of electrons to form a coordinate bond like this is called a Lewis acid. This is not a Lewis acid, this is the product. This is Lewis acid, and F minus ions which happen to donate a lone pair of electron, they will be called a Lewis base. Why? That's the definition of Lewis acid and base. Lone pair donor is Lewis base and lone pair acceptor is Lewis acid. So this is a Lewis acid. Because of incomplete octet, it is Lewis acid. Consider the compounds BCl3 and CCl4. How will they behave with water? Justify. Actually, BCl3 reacts very vigorously with water. Okay, it forms boric acid and hydrochloric acid. Wow, it releases HCl. Yes, it releases HCl. And what about CCl4? CCl4 doesn't react at all. How horrible. Yes, CCl4 plus H2O. You find no reaction at all at room temperature and pressure. With steam, superheated steam under drastic conditions around 500, 600 degrees Celsius, you find some reaction happens, but that is irrelevant here, that is not being asked. So in general, CCl4 doesn't react with water under normal condition. Bilkul. And BCl3 reacts very easily and vigorously. First, this is the first part. How will they behave? This is how they behave. Justify. We will justify. What happens? What happens is this, my dear. If you look at BCl3, BCl3 contains boron, B for boron and B for beggars. What do you mean? Boron has an incomplete octet of electron. It has only 2 plus 2 plus 2, 6 valence electrons. And it is always looking forward to 2 more electrons, and suddenly you find you add water. Water, although it's a simple molecule, but water always keeps on feeling rich because it has 2 lone pair of electrons. And boron, the moment it sees water, it says, oh my God, for heaven's sake, give me something. It says, fine, I have a lone pair, I'll give you a lone pair. BCl3 is such a huge molecule, water is such a small molecule. But if you have passion for donation and for service, even if you're small, you can do a very good job. Water donates its lone pair of electrons. Boron shamelessly accepts it. And what you get is this, B, Cl, 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 and O, H, H plus, like this. Boron acquires a negative charge because it has accepted a lone pair of electron, formal negative charge, only formal charge, not actual charge, and oxygen gets a formal charge of +1. Now starts the real fun. The moment boron gets a gain, chlorines also feel that, I am more electronegative, says chlorine atom. Boron, now that you are rich and you have electrons, I will steal your electrons and I will run away. How shameless. Yes, this is what chlorines say. We will run away and we will take your electron also. So what is happening is, if they run away, boron again would be left with just this much. H, H, it's like this. But when they are running away, the fun part is, hydrogens say, oh, come on, they are running away, we'll catch them. And suddenly, hydrogens also jump on them. And because they jump, one hydrogen jumps up and it tries to catch chlorine atoms. It tries to snatch. Now, hydrogen can jump only when it leaves its own electrons. So the poor hydrogen, it leaves its own electrons with oxygen. With bare hands, no electrons, hydrogen jumps and takes away this electron which is being stolen by Cl atom. Cl again is left with 3 lone pairs. One was being shared by hydrogen here. Since H has jumped here, it takes away 1 electron pair from Cl. Oxygen again, since 1 lone pair is there, it has taken 1 from H. O has 2 lone pairs like this. This is a reaction. Yes, this is a reaction. Please note, in BCl3, 1 Cl has been replaced by 1 OH group. Wow, that is fantastic. Yes, it is fantastic. The same reaction can be repeated twice and thrice. And repeated 2 more times, you get B, OH, OH, and OH. You get 3 hydroxides like this. And if you have 3 hydroxides like this, this, my dear, is your good old and very lovely boric acid. This is the source of reaction here. With complete details of mechanism, I have explained you why this reaction happens. But all of this begins with incomplete octet of boron. Boron is able to interact with water. Boron is able to react with water because boron was hypovalent, its octet was incomplete. If you consider CCl4, you would notice that both carbon and chlorine have complete octets. There is no place for carbon to accept a lone pair of electrons from water molecules. It is a second period element. Carbon also cannot expand its own octet. Since there is no place for lone pairs to be accepted, CCl4 cannot function as a Lewis acid. Yes, it cannot begin to react with water. And that's why, my dears, it doesn't react with water. So this is also a very beautiful reason why CCl4 is inert towards water, while BCl3 reacts very vigorously with water because of incomplete octet of boron and complete octet of carbon. Is boric acid a protic acid? Explain. What is a protic acid? A protic acid is something which donates H plus or a proton. Protic means donation of a proton. Proton means H plus. Now, boric acid has a formula B, OH, OH, OH. Does it release H plus? Actually, it doesn't. You know what happens? Boric acid contains boron atom. And as I said, B for beggar, B for boron. Boron, although it is rich, but it always has beggarly feelings. It says, you know, I have nothing. So what happens is, again, it asks, give me, for heaven's sake, give me some electrons. And water, being more considerate, donates a lone pair of electrons. Wow. What happens? You get B, OH, 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 OHH. Now, water has donated one lone pair of electrons like this. This is there. And what happens is, now oxygen, because it is getting plus charge, oxygen is irritated, it takes away one electron like this. Yeah, it takes, and it pushes away H plus. So I am left with OH, 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 OH minus and H plus. This is one H plus which can be donated like this. But that is why, fine, you know, it appears as if boric acid is acting as an acid. But has BOH whole thrice itself released an electron? No. They are acting as an acid not by giving up their own H plus, they are acting as an acid by accepting one OH minus from water molecule. From H2O, you have pushed off H plus, that means you have taken away OH minus. So, since boric acid functions as an acid by accepting OH minus and not by releasing H plus, it is not really a protic acid. But yes, it is a Lewis acid. What happens when boric acid is heated? Now, if you heat boric acid, what is boric acid? It is H3BO3, and this is also called ortho boric acid. You heat it to around 140 degrees Celsius. Okay, it loses some water and it forms metaboric acid, HBO2 n times. Heat it a little more, say around 180 degrees Celsius. You get H2B4O7 pyroboric acid. And if you make red heat, this is above 500 Kelvin, around 530 Kelvin or so. It loses water completely to form polymeric solid of B2O3 or anhydrous boron oxide. This, dears, is the action of heat on boric acid. Right reactions to justify the amphoteric nature of aluminium. Aluminium is a wonderful substance. Does it show amphoteric nature? Yes. And how does aluminium metal also reacts with acids as well as bases? Aluminium oxide also can react with acids as well as bases. They have asked us the amphoteric nature of not aluminium oxide but metallic aluminium. So let me show you that aluminium can react with acids very well, and can it react with a base very well. What does it give? It gives you a salt, AlCl3 plus 3 by 2H2. Lovely. And in case of NaOH, well, you just need some water. You find NaAlO2, sodium metaluminate. And again, you get some hydrogen. Wow. This is the case? Yes, this is the case. Aluminium metal can dissolve in acid as well as base. Please note, mostly metals dissolve in acids, but metals do not react with base at all. Aluminium, since it reacts with acid as well as base, you can say that it shows amphoteric nature. One extra information. This is about aluminium. Can we also know about aluminium oxide? Yes, or aluminium hydroxide? Very well. If you have aluminium hydroxide and you take acid or you take a base, you find that aluminium can react, aluminium hydroxide can react with acids to form salt, indeed. So since it is reacting with acid to form salt, it behaves like a base, fine. And in case you have a base, it can again react to give you something like this, a complex. Actually, you can write either this or you could write NaAlO2 plus 2H2O. This can very easily decompose to give you sodium metaluminate, again a salt. So, it reacts with a base to give you a salt, yes. So, aluminium hydroxide can react with acid also and can react with base also, and in both cases it gives you two different salts. Ultimately, that means aluminium hydroxide can behave both as an acid and as a base. Yes, it is amphoteric. Yes, what is amphoteric? Anything which can, with acids, if something behaves as a base, but with a base, if it's the same thing behaves as an acid, then that substance is said to be amphoteric, and this is very clearly shown by aluminium as well as aluminium hydroxide. So both aluminium as well as its hydroxide show amphoteric nature. What are electron deficient compounds? Compounds which do not have a complete octet of electrons in their outermost orbit are said to be electron deficient compounds. Are BCl3 and SiCl4 electron deficient species? Explain. So just take a look at BCl3. If you draw the structure of BCl3, that would be B, Cl, Cl, Cl. If you count the electrons, 2 plus 2 plus 2, you have 6 valence electrons. This is hypovalent. That means it has less than 8 valence electrons. That is why. Is it electron deficient? Yes, it is electron deficient because it has an incomplete octet of electrons. And such species are also Lewis acids. They have a tendency to beg and ask other molecules or species for a lone pair of electrons. Is SiCl4 electron deficient? Well, if you use only this much as a criteria, SiCl4 also may be counted as something which has a complete octet of electrons. And since it has a complete octet of electrons, people would tend to say that SiCl4 should not be an electron deficient compound. It is not hypovalent. Yes, it is not. And by classical means, it is not an electron deficient compound because it has an incomplete octet. Although, just, it is a little mischievous, but let me just point out, this is indeed a Lewis acid. Silicon, because of attachment to 4 chlorine atoms, is sufficiently electron deficient. It has empty d orbitals in which it can accept a lone pair of electrons. Because of that, it tends to react with water, unlike CCl4. But that is a different story. For this question, the classical answer is that because of incomplete octet, this is electron deficient and that one is not. So we will just go with that so that you're not confused. But that actually is just half the truth. Write the resonance structures of carbonate and bicarbonate. Beautiful. Carbonate ions are very striking. They have this resonance structure, and there is no special greatness attached to the top atom like this. This is what we have. These are the three contributing structures of carbonate ions, all equally contributing. What about bicarbonate? My dears, if you tend to attach one hydrogen here, you find that the extent of resonance becomes limited. Why? You could have a double bond here or there, but this OH remains unaffected. It is just the way it is. Only this much. The resonance is limited to these two oxygen atoms or CO bonds. These are the structures of carbonate and bicarbonate ions. What is the state of hybridization of carbon in carbonate? In carbonate, you have carbon as sp2 hybridized. How do I do that? Well, just draw a structure and you would find 1, 2, 3, 3 sigma bonds, no lone pairs. Steric number is 3, so sp2 hybridization. In diamonds, you have tetrahedrally linked carbon, and carbon is linked to 4 other carbons, each carbon to 4 other carbons. So that way you have sp3 hybrid carbons in diamond. In layer structure of graphite, you have sp2 hybrid carbon atoms. Wow, that is the case? Yes, my dears, that is the case. Explain the difference between the properties of diamond and graphite on the basis of their structures. Just look at the comparison between diamond and graphite on the basis of their structures. Diamond has a 3D covalent network structure in which each diamond has a tetrahedral geometry around itself, and diamond after carbon after carbon after carbon is linked tetrahedrally. So it is a crystalline structure, a rigid covalent bond network. Yes, it is. All the atoms are sp3 hybridized, geometry around each carbon is tetrahedral, and of course there are no free electrons, so this is a bad conductor of electricity. When it comes to graphite, graphite has layers of graphene, hexagonal rings of carbon, polymeric hexagonal rings, flat rings, infinite structures like this, and one layer on other layer on the other layer. That is where it is arranged. The layers can slip over the other, so it's a soft layered structure. Carbon is sp2 hybridized, geometry is planar around each carbon, and it is a very good conductor of electricity, and especially in a direction parallel to the layers. One more thing I would like to add, graphite is a bad conductor of heat, and very surprisingly, diamond is a very good conductor of heat. So diamond is a good conductor of heat, but a bad conductor of electricity. Graphite is exactly the opposite. It is a bad conductor of heat, but a good conductor of electricity. Rationalize the given statements and give chemical reactions. Okay, lead chloride reacts with chlorine to give PbCl4. Now, first of all, let me give the reaction to you. PbCl2 plus Cl2 gives PbCl4. Is this possible? Yes, it is possible. First of all, you have to have the reaction. This is the reaction. What happens here? Lead is in +2 state. Chlorine is a good oxidizing agent. It oxidizes PbCl2 and it pushes PbCl2 to give you PbCl4. Please note, because of inert pair effect, PbCl4 is not very stable. Since chlorine does manage to push PbCl2 and it does manage to generate PbCl4, because PbCl4 is not very stable, the reaction is reversible, but nonetheless, this reaction can happen. Lead 4 chloride is highly unstable towards heat. Yes, it is. If you have PbCl4 and if you happen to heat it, it will decompose in PbCl2 and chlorine. Why? Again, because of inert pair effect, lead is very unstable in +4 state. On heating, you are making it more reactive. You are trying to break bonds. Do bonds break? Yes, they do break. And not just that, it oxidizes Cl- to chlorine, and lead +2 gets reduced. Sorry, lead +4 gets reduced from +4 to +2. And the motivating factor of this is inert pair effect. Lead is more stable in lower oxidation state +2 as compared to the higher oxidation state of +4. Lead is not known to form PbI4. Why PbI4 is not formed? Because I- is a good reducing agent. Okay, so I- is very easily oxidized to iodine. And lead +4 is a very powerful oxidizing agent. It is very easily reduced to +2. An oxidizing agent and a reducing agent cannot stay together. In case if somebody manages to get PbI4, it will immediately decompose. Lead from +4 gets reduced to +2. And iodine from -1 gets oxidized to 0. So this will happen even at room temperature. And since PbI4 spontaneously decomposes at room temperature to PbI2 and I2, PbI4 obviously would not be stable because its cation reacts with anion itself. Since they internally react with each other, they cannot form a compound very naturally. Suggest the reasons why BF bond lengths in BF3 and BF4 minus differ. In BF3, there is a small beautiful aspect. See, this looks like the structure, but what happens is a little different. Boron has an empty p orbital, okay? And fluorines have a lone pair. Yes, they do. So what happens is that see, this is something that happens. Right? So you find that this electron cloud, there is significant delocalization from this side, and because of this delocalization, see, there are lone pairs here. Each fluorine has a lone pair, a lone pair, a lone pair, and a lone pair. And this lone pair shares itself with boron. This also. There is extensive what you call as p-pi back bonding between lone pairs on fluorine atoms and the empty p orbital of boron. And this gives a partial pi bond between boron and F atoms. So that means it is not just a single bond, there is also a slight touch of a double bond. And bond order increases, yes. And because bond order increases, bond length slightly decreases. So this has, first of all, this boron is sp2 hybridized, yes. And this bond order is not just one. Because of this back bonding, the bond order has become more than one, and higher the bond order, shorter is the bond length. In case of BF4 minus, please note that the hybridization is sp3. Hybridization of boron is sp3. There is no back bonding, there is no pi bond. Bond order is purely one. There is only strictly a single bond between boron and fluorine, which has a length 143. But when there is a partial pi bond, the bond length decreases from 143 to 130 picometer in BF3. That, my dears, is the reason. If BCl bond has a dipole moment, explain why BCl3 molecule has a zero dipole moment. For this, first point you must note is that dipole moment is a vector quantity. What? Yes, dipole moment is a vector quantity. And we draw the dipole moments in such a way that they are shown in the direction of displacement of electrons. Okay? Now, which is more electronegative, boron or chlorine? Very obviously, chlorines are more electronegative. So, electrons are pulled away in this direction. Yes. 1, 2, 3. And since they are being pulled away in different directions, actually, if you just take this diagram, they are being pulled away very symmetrically with angles of 120 degrees each in mutually opposite directions. And if you count the net dipole moment comes out to be the overall vector sum, which is 0. So since dipole moments of individual bonds, They are called bond moments. Since bond moments cancel out because of trigonal planar geometry of BCl3, the overall molecule has a zero dipole moment. Aluminium trifluoride is insoluble in anhydrous HF, but dissolves on addition of NaF. Aluminium trifluoride precipitates out of the resulting solution when gaseous BF3 is bubbled through it. Give reasons. Now, let's take a look at this one by one. A good question actually. It says, first of all, it gives you data that aluminium trifluoride is insoluble in anhydrous HF. Fine. What does it mean? AlF3 solid, if you add. Now, please understand, many times, many substances are soluble or insoluble in water also. There are multiple reasons. AlF3 solid and HF. If you add them like this, apparently it looks like that there is no significant reaction, right? But dissolves on addition of NaF. This plus HF, no reaction, no dissolution also, nothing. But if you take AlF3, please note, when you're talking about anhydrous HF, that means HF is covalent, it is not dissociated. But in case you're having sodium fluoride, NaF, can you appreciate that this sodium fluoride, I mean, it has sodium ions and fluoride ions separate, obviously. There are cations and anions. And this F minus can always donate a lone pair of electrons to AlF3. Wow. Is that possible? Why not? And actually, you would get something very lovely. You will get AlF6 3 minus in solution. Okay, very interesting. This is a complex. Yes, Na3AlF6 you might have heard about. Cryolite is a very popular ore which was originally found in Greenland. It is used in it was used in metallurgy of aluminium. Nowadays it is artificially synthesized like this. So AlF3 would undergo a complexation reaction with NaF and it would form AlF6 3 minus. But for this, F minus has to donate a lone pair of electrons. If F minus has to donate a lone pair of electrons, F minus should possess a lone pair of electrons extra. Apparently, there were 3 lone pairs on HF, on fluorine in HF, but there was no negative charge. Since there was no significant negative charge, the tendency of donation of lone pair was not very high with HF or with fluorine in HF. The moment you convert this to NaF, Lewis basic strength, the tendency to donate lone pair increases. And because it donates, because it has negative charge, it says take electrons, take negative charge. It forms a complex. It dissolves. Lovely. Aluminium trifluoride precipitate out. Equilibrium shifts backwards. AlF3 precipitates out when gaseous BF3 is bubbled through it. That also is very lovely. Just imagine BF3 being exposed to this. Now, there are 2 Lewis acids, AlF3 and BF3, and F minus now has a choice. Why? F minus just has to donate lone pairs. Whomsoever is willing to take lone pairs, as a matter of fact, snatch lone pairs. It is much easier. And boron is much smaller in size than aluminium. They are in the same family. Boron is the younger brother, right? The smaller. And smaller and younger brothers say, more choosy. And whenever there is a choice, no, we want lone pair. Aluminium says, boron says, no, I want lone pair. What would aluminium do? Fine. Okay, boron, you're younger, you take the lone pair. So this is the way it happens. So, you find that this donates a lone pair and BF3 accepts it. And it actually starts forming BF4 minus, which is much more stable than AlF6 3 minus. Because boron, being a smaller atom, has greater polarizing power. It's a stronger Lewis acid. So it takes away F minus. If it takes away F minus, the equilibrium shifts backwards as per Le Chatelier's principle. And as equilibrium shifts backwards, again you find along with AlF3 gets precipitated exactly in accordance with Le Chatelier's principle from chemical equilibrium. That, my dears, is the reason why F minus pushes it this side and adding BF3 pushes it back. Beautiful question. Take a look. Suggest a reason as to why carbon monoxide is poisonous. Why do you think it's poisonous? Carbon monoxide is an excellent Lewis base or a so-called ligand. It can donate a lone pair of electrons very strongly and it can form very stable bonds with a number of molecules, yeah, atoms or ions also. A very good example is hemoglobin. I hope you remember what is hemoglobin. Something which makes your blood red. It's literally in your blood. It gives you red color, right? And hemoglobin actually contains iron atom at the center. And this iron atom in hemoglobin forms an unstable complex with oxygen. Why? When you're breathing, you're taking oxygen or air within your lungs. And within your lungs, your heart is always pumping blood. So this blood comes in contact with oxygen from atmosphere. Why does this oxygen get dissolved in blood? Oxygen is not very soluble in water anyways. What happens is that within blood there is a molecule called hemoglobin, and within hemoglobin there is an ion of iron. There is ferrous or ferric ion which is sitting within hemoglobin, and this iron atom accepts a lone pair and forms a temporary, a very unstable kind of a complex with oxygen. Oh, that's a bad thing. It's a very good thing that the complex is unstable. Why? What happens is then blood, that blood exits lungs. That blood is pumped to every corner of the body. And as this blood reaches different cells, because this complex is unstable, it decomposes. It gives away oxygen back. Not only it gives away oxygen, it takes back carbon dioxide. Wow. And it carries it back to lungs and releases carbon dioxide there. This is the way you actually breathe, or rather your breath is carried to every cell of your body. This is the source of energy which keeps every cell of your body alive. And what happens if you take carbon monoxide? If you breathe carbon monoxide, this carbon monoxide has great love for iron. It forms a very stable complex with iron. Now you may feel that stable complexes are good. No, not in this case. Because now once carbon monoxide has formed a bond with iron, it is stuck. It does not leave iron. But iron was supposed to carry oxygen, yes. And as long as carbon monoxide is sitting out there, iron cannot carry any oxygen. Yes, it can't. What happens? Actually, that hemoglobin molecule is now a waste. It is junk. It is useless. Because it cannot carry oxygen, and you cannot immediately or instantaneously generate hemoglobin molecule. Body takes significant time in generating hemoglobin molecules. What happens? That hemoglobin is gone. That RBC is dead. And if you keep on inhaling more and more carbon monoxide, you are actually literally killing the capacity of your blood to carry oxygen. And this loss of oxygen, that means every cell in the body would be deprived of oxygen, and this is something which can easily cause death. It's very dangerous. That's why carbon monoxide is poisonous. Much worse, carbon monoxide has no smell. It has no color. So you won't be able to detect also that there's carbon monoxide actually entering your breath till you begin to suffocate. And unless there is blood transfusion, fresh blood is injected immediately, the person would unfortunately die. Bad enough, be careful. How is excessive content of carbon dioxide responsible for global warming? Actually, if the content of, or if the percentage of carbon dioxide in the atmosphere increases, you know what happens? Carbon dioxide is a gas which is termed typically as a greenhouse gas. What do you mean by greenhouse gas? What happens is this. Say, if this is Earth, right? And above Earth, you have a lovely atmosphere. This is atmosphere. Now, atmosphere has different layers and all, you know that. Huh? We have stratosphere and exosphere and, you know, all kinds of spheres. Fine, good enough. Now, what happens is, as sunlight comes in, as sunlight comes in and penetrates this atmosphere and reaches Earth, some of it is reflected, etc., etc. Part of it reaches here, fine. The one which is reflected from Earth, it again has to pass through atmosphere, and then as it passes through, some of it goes back in atmosphere. Yes. But do you understand that atmosphere also is comprised of various molecules of air? Most of it is O2 and N2, right? Part of this heat is absorbed by O2 and N2, and they do not allow this heat to escape out in the atmosphere. Yeah, in the vacuum or in the space, right? And that is why, my dears, Earth remains warm even in those zones where there is no immediate sunlight or where there is night. Okay, that's useful. That's very, very useful. But unfortunately, if the content of carbon dioxide in air increases, even if it increases very slightly, carbon dioxide has a property that it tends to absorb the radiation. The radiation which is leaving Earth, which is going out from Earth, it tends to absorb this radiation much more than O2 or N2, which are the actual components of real air in the atmosphere. So what happens? If CO2 content in the atmosphere would increase, that would mean that now the atmosphere is going to trap more carbon dioxide, more heat than necessary. Whatever the heat was being absorbed by the atmosphere now begins to absorb more heat, because the capacity of CO2 to absorb this kind of a heat is much more as compared to O2 or N2. That is the reason that if CO2 tends to absorb more heat, and if the percentage of CO2 in atmosphere increases, since atmosphere will begin to absorb more heat, Earth would become warmer, because it is not allowing that heat to escape back into the space. And that, my dear, would be the reason for global warming. In short, if you want to say this in one sentence, we say CO2 is a greenhouse gas. This phenomenon is called greenhouse effect. And we say that CO2 is a greenhouse gas. So, if it is present in greater quantity, it will absorb more heat and cause global warming. That's the reason. For those who want a written answer, you can take a screenshot and just feel good about this. Explain the structures of diborane and boric acid. Wow. Let's take a look first. Diborane. Diborane is typically B2H6. B2H6 contains 2 bonds of boron and 4 bonds of hydrogen. All these 6 atoms are in one plane. And the most striking are the bridging bonds. There are 2 bonds of hydrogen. What? Hydrogen is forming 2 bonds? What nonsense is this? That means, is hydrogen expanding its duplet? No. That is the strangest activity actually. What happens is that if, say, this boron has a BH bond, then electron of this BH bond is also attracted by the other boron atom like this. What you get is the so-called 3-center 2-electron bonds. What does it mean? There are only 2 electrons in a BH bond, but those 2 electrons are also pulled on this side. So it's 1, 2, 3. It's a 3-center 2-electron bond. Oh my God. And this is in a plane perpendicular to the other plane. Okay. So there is one bond like this and there is another bond like this. Oh wow. Wonderful. They look like bananas. Yeah. And that is why sometimes people even call them banana bonds. I'll just draw them back for you. like this, you can draw them. These are called bridging hydrogens. And these are called terminal hydrogens. So overall, you would see that this is this BH inside. It is a perpendicular plane. So this is the way you should be able to view overall structure of diborane. Two mutually perpendicular planes, 4 normal BH bonds, and terminal bonds are stronger bonds and shorter. These bonds are stronger and shorter. These are longer and weaker. Why? They are weaker because bond order is only half. This is a full bond. This is half, 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 half. That is the way you should count them. This, my dears, is the structure of diborane. This bond angle HBH, terminal HBH bond angle is close to 120 degrees and bridging HBH angle is close to 90 degrees. Now let's talk about boric acid. What is boric acid? Boric acid, also called orthoboric acid, is H3BO3. It has boron, it has O, O and O, it has H, H and H. Lone pairs like this. And it might appear that this could be a zigzag molecule, but no. Boric acid is trigonal planar around boron. And also please note, the funny part of boric acid is that each of these oxygen atoms contains these lone pairs. Na? There are lone pairs you can see. So one lone pair on each O atom undergoes P-pi back bonding with boron atom. Oh my God, is that so? Yes, it forms P-pi back bonding with boron atom. And because of this, my dears, this, not only this is planar, because of this, oxygens also become sp2 hybridized and the entire boric acid molecule is perfectly a planar molecule. So O atoms are also sp2 hybrid and all planar molecule. This, my dear, is the structure of boric acid. What happens when borax is heated strongly? First of all, if you take a small piece of borax and heat it, it swells like a popcorn. And if you keep on heating it, ultimately it contracts. And when it contracts, it collapses to a very glass-like, beautiful, transparent bead. Oh, is that so? What happens? First of all, you should know what is borax. Borax is Na2B4O7.10H2. Notice that 2, 4, 7, 10. They are in ascending order, the numbers. And if you heat this, what happened? First of all, it swells up like a popcorn. On further heating, keep on heating, it collapses. When it swells up, it is fluffy. When it collapses, it becomes solid, shiny, transparent, glassy bead. Transparent, mark my words. What you get is NaBO2 plus B2O3. This is glassy bead. This is what you obtain on strongly heating borax. Water, of course, evaporates. Hardly a mystery. That's it. When boric acid is added to water, you know, something very funny happens. Boric acid is such a stupid acid, you know. It does not release H+. Rather, it accepts OH- and wants to release H+. You can write it like this, or the same reaction can be written as H3BO3 plus 2 H2O. You add 1 H2O on both the sides. Why? Instead of H plus, there are people who love to write H3O plus. You can well do that. That's perfectly fine. But please note, equilibrium is shifted largely backwards. To a very small extent, it is able to release H plus. But yes, it does. And this is the reaction. This is what happens when boric acid is added to water. It becomes very slightly acidic. Aluminium is treated with dilute NaOH. Wow. When aluminium is treated with NaOH, what happens is aluminium dissolves in it. What? Yes. Aluminium dissolves in it, forming NaAlOH whole 4, and there is some quantity of hydrogen also, oh my God, which is released. If this, what I'm writing is not clear to you, I'll write it once again so that it is very clear. I hope this is cleaner. Yaps. Do we need to balance this? I presume yes. We need 4 oxygens, 3. I guess that should do. 1 NaOH, 1 oxygen and 3. Let me check hydrogens. 6 plus 1, 7. We have 3 plus 4, 7. Perfect. Done. Balanced. This is what you obtain. This is aqueous solution. And this always dissociates as NaAlO2 and 2H2. You can also break it down like this. Some people write this, some people write this. Actually, what happens is, whenever you have this, you always have some quantity of this and vice versa. So if you're writing a subjective paper, write both, no problem. If you're writing objective, any of these can be offered as the answer and either of them is the correct answer, no problem. If both are asked, only in JEE Advanced you get more than one correct. If both are asked, both are correct. This is what happens when aluminium is treated with dilute NaOH. It dissolves in dilute NaOH, liberating hydrogen and plenty of heat as well. Explain the following reactions. Silicon is heated with methyl chloride in at high temperature in the presence of copper. It's a very standard reaction. What happens is this. If you take silicon and heat this with CH3Cl, 537 Kelvin in presence of copper catalyst, you find you get methyl and chlorine groups substituted on silicon. That means you get CH3 whole twice SiCl2. This is dichloro-dimethyl silane. You also get CH3 SiCl3 and CH3 whole thrice SiCl. Trichloro-methylsilane, dichloro-dimethyl-silane, chloro-trimethyl-silane, and you also get very small quantity of CH3 whole 4 Si tetramethyl-silane as well. That is just a beautiful but arbitrary reaction. This is what happens on heating together silicon and methyl chloride. What about SiO2? What happens if SiO2 is treated with HF? Wow. Silica is fairly inert. Are you aware that HF is the only acid which can dissolve silica? It reacts with silica, forming first SiF4 plus 2H2O. But this SiF4 is quite reactive. This SiF4 can, if you have concentrated or anhydrous HF, this will further react with HF to form hydrofluorosilicic acid H2SiF6, which is a white waxy solid. Also, if no extra HF is there, SiF4 can very well react with water. It can undergo hydrolysis. And then also it can form H2SiO3 plus H2SiF6. That also is a possibility. 4 3s are 12, 2s are 12, right? And we have 4 plus 2, 6 hydrogens, and we have 6 hydrogens. This is balanced, you can see. So this SiF4 which is generated, 1 mole with 2 moles of water is generated, and this SiF4 can very well react with water to give you hydrofluorosilicic acid plus H2SiO3. So partly this hydrolysis of SiF4 can happen. But if there is excess anhydrous HF, you find that HF can directly react with SiF4 to give you H2SiF6 also. These are the reactions, my dear, which happen when silicon dioxide is treated with HF. HF can dissolve silica, and HF is the only acid which can dissolve silica. CO is heated with zinc oxide. Well, if zinc oxide is heated with CO, carbon monoxide is a popular reducing agent. It gets oxidized to CO2 and zinc oxide is reduced to metallic zinc. Wonderful reduction. Hydrated alumina, that is Al2O3.XH2O, where X is between 0 and 2. It is more than 0 but less than or equal to 2. This is hydrated alumina. If this is treated with aqueous NaOH, what you get is NaAlO2. Wow. Please note this is solid and it dissolves, giving you an aqueous solution of NaAlO2. And in addition, you get lots and lots of water plus some H2. Can you add that up? We can do that. This is X plus 1 H2. If this is X, you get one more water, you get X plus 1 water, like this. Give reasons. Concentrated nitric acid can be transported into aluminium container. Can aluminium react with nitric acid? Actually it does, but there's a catch. And what is that catch? Concentrated nitric acid passivates aluminium. What? Yes, aluminium is passivated by concentrated nitric. Please note, this is not true for dilute nitric acid, but concentrated nitric acid can be passivated by aluminium. What happens? As aluminium is treated with concentrated nitric acid, immediately aluminium is oxidized. There's a very vigorous reaction. Lots of heat is generated and nearly immediately the reaction stops. What happens is a protective coating of Al2O3 is formed on aluminium metal. The surface of metal is covered by a very thin coat, but a protective coating of Al2O3 which sticks to the surface. And that, my dear, prevents the further reaction of aluminium with any remaining nitric acid. And that is why you would find that aluminium does not react with nitric acid. As a matter of fact, it is passivated by nitric acid so well that after passivation, even if you add dilute nitric acid or other acids, aluminium would not react with any other acid as well. Fantastic. A mixture of dilute NaOH and aluminium pieces is used to open drains. You would find that there are drains which get choked. A lot of different stuffs are often drained out, and sometimes there is choking. Choking means something is stuck within the pipes and somebody actually has to go and push them, and there is no way you can actually go inside a pipe and push it. So, and that's very gross and dirty idea also. So what happens is, if you take aluminium and if you add dilute NaOH, something wonderful happens. Slowly, as they are washed down the drain, they react. And when they react, they release hydrogen gas. First of all, NaOH itself is capable of reacting with any remaining oil or grease. So it can cut through oil and grease, and that helps. Not just that, when hydrogen is generated, it is a gas, it needs a lot of volume. But it is already present in the drain, it is liberated within the drain. So that gas pushes any kind of junk or any clogging material which is choking the drain. So as that material gets pushed, the drain gets cleared out, and this is what we need. So this is why the mixture is used. Graphite is used as a lubricant. This is very interesting. Why? Actually, graphite consists of nice, beautiful, happy, hexagonal rings of sp2 hybrid carbon atoms. So what? And these layers and these rings are, attached one after the other like this, and they just continue like this. This one flat layer is known by a very beautiful name. This is called graphene. And such one layer above the other, one above the other. That way, if you join, you find when these layers are placed one above the other, they are just attracted to each other by van der Waals forces, very loosely held. And they actually give you your entire graphite. Since these two layers are only held by loose van der Waals forces, they can slip over each other. And because they can slip over each other, graphite is not very hard or rigid. It is very soft. And because of the slipping at molecular level, it can function as a lubricant. Yes. One more very interesting thing about graphite is that graphite has a very, very high melting point, more than 4,000 degrees Celsius. What does that mean? It means that graphite as a solid powder, if graphite powder is applied as a lubricant, it would never melt. It would never, and many times, if you apply something like grease as a lubricant, on heating it melts. When it melts, molten grease can just flow away from whichever portion was greased out, and again friction comes back because the lubricant goes away because it has become thinner because of heat. Graphite powder does not become thinner. Thinner means less viscous because of heat, because it is a solid powder. Efficiency of this lubricant does not change on heating, and that is why it is a very beautiful and nice lubricant, except one factor: it cannot be used as a lubricant in open systems. The system has to be closed. Why? Because otherwise, on heating, graphite can burn an oxygen to form CO or CO2. If you have closed engines, closed setups where oxygen is not entering, graphite powder is a very good lubricant. Diamond is used as an abrasive. What is abrasive? Something which is hard and rough, which is used for cutting and polishing. I live in Kota, Rajasthan, and that is a place famous for something called as Kota stone. It's a green colored stone. It's a variation of marble. It's not actually marble, it's a different stone, but ultimately it's calcium carbonate only, which is a greenish hue. You would often find Kota stone applied on, used on railway stations, etc. The fun part is, this stone is cut using diamond cutters. And when I, for the first time, observed those cutters, I had imagined something like a Sudarshan Chakra, glittering diamonds placed on one cutter. They were nothing like glittering diamonds. They were very dull black diamonds. They were raw diamonds, and they were black also, because there are diamonds which are not gem quality diamonds, and they are the ones which are used for cutting. But yes, is it used in an abrasive? Because diamond is the hardest known substance which is popular. There are scientists who claim that they have got substances harder than diamond, but very unpopular. Diamond is the most popular, hardest substance known to humans. And that is why it is used for cutting and polishing other things which otherwise are considered hard, like stone. Aluminium alloys are used to make the aircraft body. Aluminium as a metal has very less density as compared to iron. Iron has been very popular because it is sturdy, it is strong. Aluminium as a metal has a good tensile strength. It is a strong metal. At the same time, its density is significantly less than iron. And that is why if you have to fly a plane, flying a plane, a very important component is the lesser the weight, easier it is to fly. And aluminium makes sure that the weight of aircraft's body is much lesser, and that is why it is a very preferred material. Aluminium utensils should not be kept in water overnight. Why? Actually, aluminium can slowly react with water. What? Yes. If you make amalgam of aluminium, it is very much capable of reacting very vigorously with water. Actually, what happens is, Aluminium, if just left on its own, can slowly react with water to form aluminium hydroxide. It could liberate hydrogen. So if you have aluminium vessels, aluminium cooker or something, it would get, it would get corroded if you have something of this kind. And especially if you have soaps or bleaches, they are alkaline in nature and they also can dissolve some portion of some portion of aluminium or even aluminium oxide coating. So the life of the utensil will be greatly reduced. That is why it is preferred that you just let it rest in dry condition. Aluminium is used to make transmission cables. Why? Because aluminium has a reasonably good conductivity. Electrical conductivity of aluminium is high. Of course, it is not high like copper, silver or gold, but it is much cheaper than copper or silver or gold. Its density is less, the cables have lesser weight and they are more easily sometimes to hang up and carry around. Most importantly, they are cheap and at the same time, they are very good conductors of electricity, and that is why aluminium is used for making transmission cables. Good electrical conductivity, less cost and easy availability of aluminium. Explain why there is phenomenal decrease in ionization enthalpy from carbon to silicon. On moving from carbon to silicon, the size increases. Just look at this. Carbon, silicon, germanium, tin and lead. If you notice them, carbon is atomic number 6, silicon has 14, germanium is much bigger, it has 32. So there is increase of only 8 protons plus addition of 1 electronic shell. If you add 1 electronic shell, electrons have gone away from nucleus. If they have gone away from nucleus, nucleus is not able to attract them as much. It becomes easier to take them away and ionization energy decreases significantly on going from carbon to silicon. But you would understand this idea much better the moment you hear about the contrast. If you move from silicon to germanium, my God, you would find that there is increase of 18 protons. 18 protons means much more attraction now. Earlier, 14 protons were attracting the electron cloud. Now more than double, 32 protons are attracting the electron cloud. And I have just added only 1 more shell. So yes, on moving down the group, size increases. Yes, and because size increases, you find that ionization energy does not increase, actually it decreases, but the rate of decrease is not as much. Carbon to silicon, there is a sharp decrease. Silicon to germanium, the decrease is not as much, simply because the difference in atomic number, the number of protons which are added from carbon to silicon is only 8 and 1 extra shell is added, and more rapid increase in size leads to a significant decrease in ionization energy. The same can be compared by data also. Carbon to silicon, 1086 to 786. This is a sharp fall of 300 kilojoules per mole. Germanium is barely 27. 300 and the difference is just 27. This difference again, see 786, 761, 708, 715. They're all close by, and this difference is very sharp because only 8 protons added and 1 extra shell, you're going away and not attracting as much, and that is why a sharp decrease in ionization energy. How do you explain the lower atomic radius of gallium as compared to aluminium? Well, on moving from boron to aluminium, atomic number increases by 8 and 1 shell is added. But when you move from aluminium to gallium, atomic number increases by delta Z, I would say. Atomic number is typically represented by Z. I'll just correct this. Atomic number increases by 18 and again 1 shell is added. Not just that. You may say that if 18 protons are added in the nucleus, they will attract more. Yes, but 18 electrons are also added, so they should repel also. There is a problem. 10 electrons are added to D subshell. And this D subshell is not able to screen the nuclear charge properly. So, charge in the nucleus is increasing. So, attraction increases. If attraction increases, electrons are sucked in and the size should come down. Also, if atomic number is increasing, you're also adding electrons in the electronic orbit. And more electrons should have meant more repulsion, bigger size, but there is a problem. There are 10 electrons in D subshell, and D subshell electrons are diffused. They are not able to repel as much as the attraction which is increased because of 10 extra protons. So net result is the size keeps on decreasing and decreasing and decreasing, and at the end of it, the moment D block ends and gallium appears, the size becomes so small that gallium actually has a very small, it's 2 or 3 picometers less radius as compared to aluminium. Atomic number of aluminium is 13 and gallium is solid 31, and still gallium is polar because of this reason. What are allotropes? Sketch the structure of two allotropes of carbon, namely diamond and graphite. What is the impact of structure on physical properties of two allotropes? What exactly are allotropes? If a given element can exist in more than one states, what is the meaning of more than one states? Same chemical composition, but if it can exist in more than one forms where the chemical properties are different. Even the physical properties are different. Allotropes have different physical and chemical properties, but they have the same chemical composition. If this is possible for a substance, then the phenomenon is called allotropy. A very common error is sometimes people say chemical properties are same. No, chemical properties are definitely not same. Ozone is an allotrope of oxygen and they have very, very different chemical properties. Diamond is an allotrope of graphite and both of them have absolutely different chemical properties as well. Diamond has a tetrahedral structure, polymeric tetrahedral cross-linked structure. Each carbon is joined to 4 other carbon atoms. Each carbon is joined to 4 other carbon atoms and it goes on repeating like this. Graphite has hexagons, hexagonal rings, just as the rings are present in benzene, and these are fused rings. And they go on infinitely repeating, and each layer is linked to the other layer and the other layer. There are layers stacked one above the other, and these layers are attracted to each other by very loose van der Waals forces, and these layers can slip over each other. So, can we compare their properties? Yes. What is the impact of structure on physical properties of two allotropes? That's very easy. I'll just write down few physical properties which you can compare with great ease. First of all, density. Which is more dense, diamond or graphite? Graphite has layers which are kept one over the other and they are not attracted much to each other. There is significant gap in between these two layers. Same number of atoms will occupy larger volumes because of these gaps. Volume is more, the density would be less. So you have diamond has a greater density than graphite because graphite has significant gap in between the layers of graphene or the flat planar layers. A second very important factor is hardness. Hardness is something which is very, very popular. Diamond is much, much harder than graphite. Graphite is soft, you can make it powdery. Actually, it is used as a lubricant. On the other hand, diamond is so hard, it is the best possible abrasive. You can use it for cutting, polishing the hardest of the other substances, and it works very well. Third is electrical conductivity. Diamond is an absolute insulator. It has no loose electrons. It does not conduct electricity. Diamond is much, much less than, I'll use a different color so that I'm visible, and thick pen also I'm going to use. Diamond is much, much less than graphite. This is more, this is more. Oh yes, this is ugly and visible. Yes, indeed. What about thermal conductivity? That also is a very interesting property. And you find that thermal conductivity, thermal conductivity of diamond is more than graphite. Why? Very interestingly, graphite does not, graphite is a thermal insulator. Surprisingly, diamond is an excellent conductor of heat. So diamond can conduct heat but not electricity. Graphite can conduct electricity but not heat. These are very interesting 4 points of comparison between their physical properties which can be related to their structures. Classify the following oxides as neutral, acidic, basic or amphoteric. Well, we have CO, carbon monoxide happens to be a neutral oxide. Wow. You have B2O3 and SiO2. Now, boron is a non-metal and non-metal oxides are typically acidic. So, you have B2O3 as acidic oxide. Silica and carbon dioxide, CO2 also is an acidic oxide, no doubt. SiO2 is very, very debatable. At times, there are people who claim that silica is acidic. Why? Because it reacts with bases. At the same time, there is an acid called HF with which silica also react. Silica can react with acids as well as bases. Silica is classically amphoteric. Also, we have the rule that all the oxides of metalloids are amphoteric. Silicon is a metalloid, its oxide would be amphoteric. Al2O3 as an exception, because aluminium, although it is a metal, but aluminium, tin and lead, these oxides are typically amphoteric from P block to aluminium. Then we have PbO2 which is also amphoteric. Tl2O3 is basic. Oh wow. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We have done the classification. This is the answer. Write the suitable chemical reactions to show their nature. Well, CO plus HCl, no reaction. And CO plus aqueous NaOH, no reaction. So we say that CO is neutral because it does not react with either acid or base. B2O3, it is an acidic oxide. Why? Because it reacts with a base. You take NaOH and you just heat it. Okay, it forms NaBO2, sodium metaborate, like this. So acid and base react to give you salt and water. So B2O3 is typically an acidic oxide. If you take silica, silica plus NaOH in a very similar fashion can give you Na2SiO3 plus H2O. Yes, indeed. At the same time, silica plus HF can give you SiF4 plus H2O. So you can see that silica can react with base. It can also react with an acid to give you salt and water. So silica can function as an acid as well as a base. It is acidic with a basic oxide. It is basic with an acidic oxide, with an acid directly. So you can say that silica typically shows amphoteric nature. I repeat, although there are people who strongly believe, which is not very correct, I believe, that silica is acidic in nature. How can I justify what I'm saying? It's very simple. See, metalloids like silicon, germanium, in general, whenever you have any metalloid, oxides of metalloids are classically regarded as amphoteric oxides only. As non-metal oxides, acidic. Metal oxides, usually basic, and metalloid oxides, usually amphoteric. This is typically the trend. CO2. CO2 plus NaOH will give you NaHCO3. With more NaOH, it can give you even Na2CO3 plus water. So CO2 can react with base to form salts, but CO2 plus HCl, any acid, there is no reaction. So CO2 reacts with the base but does not react with an acid. Perfect. So it is an acidic oxide because it reacts with the base. Makes sense. Aluminium oxide, this plus HCl, Al2O3 plus NaOH. This is the fun part. What do you get? You get AlCl3 plus. So aluminium oxide reacts with an acid to form salt and water. Indeed. Aluminium oxide also reacts with a base to form a salt and water. Once again, yes. So what is aluminium oxide? Aluminium oxide becomes amphoteric in nature because with a strong acid, it behaves like a base. With a strong base, it behaves like an acid. And the substances which do this are typically and classically termed as amphoteric. PbO2. PbO2 plus NaOH can give you Na2PbO3 plus H2O. Just like silica, SiO2, same family PbO2. It can react to give you sodium plumbate. Yes, very much. The same PbO2, if you react with, say, HF, will give you PbF4 plus 2H2O. Reactions are very similar, on very similar track. But I repeat, there are people who point out that PbO2 is amphoteric, but silica is acidic. I'm saying this because very popularly silica is quoted as acidic in popular, common, low-grade literature. Unfortunately, silica is best regarded as amphoteric only. Tl2O3. Tl2O3 is a classical base. With HCl, it can give you TlCl3, or with HF, it can give you TlF3 also. But same Tl2O3, if you add NaOH, you would get no reaction. It won't react at all. In some of the reactions, thallium resembles aluminium, whereas in others it resembles with group 1 metals. Yes. Support this statement by giving some evidences. Let's try. You have to appreciate that thallium can show two different oxidation states. It can show +1 as well as +3. Tl plus. The thallium shows +1 as well as +3 states. You have T8 plus and Tl3 plus. So wherever thallium tends to show +3, it would resemble something like aluminium. And whenever it shows +1, it would resemble something like sodium or group 1 elements. For example, it can form TlCl just like NaCl, or TLI just like NaI. At the same time, AlCl3 and you get TlCl3. So yes, are there similarities? There are very much similarities. You have Al2O3 and thallium can form Tl2O3 as well. So yes, there are similarities, but also please don't forget that there are differences as well. But only similarities have been expected here, giving examples. So we have given similarities with examples. When a metal X is treated with sodium hydroxide, we should note down such questions. When a metal X is treated with sodium hydroxide. Now please note this is a metal. A white precipitate A is obtained. A white precipitate A is obtained, which is soluble in excess NaOH. Wow. Excess NaOH, this dissolves, giving an aqueous solution B. And it is a complex. Well, B is a complex. How lovely. And since excess NaOH is giving it, it should be preferably a hydroxo complex. Compound A is soluble in dilute HCl to form a compound C. Now, if I add dilute HCl, it becomes soluble to form a compound C, which must be an aqueous solution, of course. A, when heated strongly, gives D, okay, which is used to extract the metal. You heat strongly, you get D, which is used for extraction of metal. Identify X and ABCD, write suitable equations to support their identities. Can we do that? Of course we can do. Extract metal. Now first of all, you see, the most signature hint in the entire question is this. You have a metal which dissolves in NaOH. Now metals normally do not react with NaOH at all. If you take things like iron, they have no reaction with, in general, any NaOH or a base. Which metals can react with NaOH? Amphoteric metals like aluminium, tin, lead. These are the metals. Now, this dissolves in NaOH, it gives you a white precipitate. Yeah, it rather reacts with NaOH to give a white precipitate, fine, which is soluble in excess. Again, a hint of amphoteric nature. This precipitate, it must be a hydroxide precipitate, and this precipitate dissolves in NaOH, fancy. It also dissolves in HCl, which is again very beautiful and very, very good. Great. I have a hydroxide which is white, which is amphoteric in nature. I am also told that it is soluble in dilute HCl. Now all this hints towards aluminium. Why? Just write aluminium and see. Now in these kinds of word problems, one idea is required, and the moment you get amphoteric nature, hydroxide dissolving in NaOH forming hydroxo complex, this dissolving in HCl, this classically and typically looks like a +2 or +3 oxide. Why not +4? A +4 oxide will have a problem because if you take things like PbO2 and SnO2, they would find it difficult to dissolve in HCl directly without a redox reaction. But aluminium can dissolve very beautifully. So we eliminate those nonsensical options and we get aluminium as a potential candidate. Let me try this out. Say if X is equal to aluminium, this would become, A becomes aluminium hydroxide, B becomes NaAlOH whole 4. What is the reaction? This is a very easy reaction, yes. AlOH whole thrice on drying will give you Al2O3 plus H2. Water vapor will evaporate and I just get this. Makes sense. AlOH whole thrice plus 3 HCl will give me AlCl3 plus 3 H2. So yes, I have that reaction also, no problem. And Al2O3, molten alumina, is dissolved in cryolite and electrolyzed to obtain metallic aluminium. That also, my dears, is a very true reaction. And how would aluminium react to give you aluminium hydroxide? Aluminium plus NaOH. Apparently, this is alkaline medium plus H2O. Now, this is giving me AlOH whole thrice plus 3/2 H2. I have written this reaction for the sake of writing it. It is my duty to inform you that the lovely NCERT has framed this wrong question. No metal will give you metal hydroxide on treating with NaOH. As a matter of fact, if aluminium and NaOH react, it directly gives you this complex. You get hydrogen and the complex directly. You don't first see metallic aluminium turning white, giving you aluminium hydroxide. That's a very wrong idea. But it is legendary and celebrated NCERT. They are free to change even God's creation and they manipulate chemistry like anything. So I have presented a solution which is commonly given in guides. And I cannot, as a student of chemistry, I cannot help getting irritated that it is a blasphemy. I mean, what they've done is sheer nonsense. I have written a reaction. And I have just mentioned it at the end with great frustration. Let me point out, this is not the correct reaction. This aluminium plus water giving aluminium hydroxide plus hydrogen. No, they are dissolving this in NaOH. Please note, there is no NaOH required here. As a matter of fact, is this reaction impossible? Such a reaction is possible if you take aluminium amalgam and add water. It is possible. They have not done that. They have added NaOH. If you add NaOH, you will never obtain white gelatinous precipitate. Doesn't happen. It just doesn't happen. A solid water insoluble aluminium would never give you with NaOH aluminium hydroxide. It would directly give you this complex. But again, NCERT is not about logic. It is not about chemistry. It is about the ego of the people who wrote it. So there we have it. This is the Bible. Take it and feel happy. Let me go ahead. What do you understand by inert pair effect, allotropy and catenation? Inert pair effect, it is a very simple and beautiful phenomenon. The tendency of p block elements, to preferably remain in their lower oxidation state increases on moving down the group. What? Let me repeat. In p block, elements have a tendency to become more stable in their lower oxidation state on moving down the group in p block. That means NS2, NP1 to 6. This is typically a p block configuration. In this, NS2 tends to become inert. This pair of electrons tends to become relatively more inert on moving down the group, and this phenomenon is called inert pair effect. And because of this inert pair effect, in 6th period, thallium plus 3 is not as stable as thallium plus 1. Lead plus 4 is not as stable as lead plus 2. These are the preferred oxidation states because 6s2 electrons in thallium and lead prefers not to react. It becomes inert, and that is why we call this inert pair effect. What is allotropy? If a substance, often an element, if an element can exist in more than one forms in such a way that chemical composition is the same, but physical and chemical properties become different, like diamond and graphite, then the substance is said to show allotropy. Please note, allotropes have different physical properties. They also have different chemical properties. There may be some similarities, but there are always notable differences. So if the same element can be present in more than one forms such that chemical composition is same, but physical and chemical properties are different, then that substance is said to show allotropy. Examples being rhombic and monoclinic sulfur. A second example, a very famous example, is diamond and graphite. Catenation, C part. The tendency of direct bonding between atoms of same element. The tendency of direct bonding between atoms of same element to form long chains is said to be catenation. Master of catenation is carbon. Nobody beats carbon because carbon can just go on forming millions of carbon chains. Chains containing millions of carbon atoms one after the other, and that, my dears, is very unique property of carbon and carbon alone. Oxygens hate each other. Not more than 3 can combine, and even if 3 oxygen atoms combine, they give you something like ozone, which is very unstable and very, very reactive. So in general, atoms do not like forming bonds with each other, but when they do, they are a family, and the family has great strength, and that's why we find catenation as a very unique property of carbon. For those who want a written answer, these are the answer. Take a screenshot and just feel happy about this in case you need this. A certain salt X gives the following results. Okay, let's read. Its aqueous solution is alkaline to litmus. Fine. X is alkaline to litmus, and it is a salt. Let's not forget this. Then it swells up to a glassy material on strong heating. Strong heat, and it swells. Now we know only one thing which swells on heating, and that is borax. But let's take a look. When concentrated sulfuric acid is added to a hot solution of X, white crystals of an acid Z separate out. Very interesting. Write equations for all the above reactions and identify X, Y, and Z. The moment, my dears, you said swells up to a glassy material, we reveal that this is borax. What is borax? The X has to be nothing but Na2B4O7.10H2. Okay. If you heat this, it swells, giving NaBO2 plus B2O3, a very intimate mixture of this, which is nothing but the glassy bead, the glassy substance in general. And this is Y. Material. The shape always may not be a bead-like, so it is glassy material. And then concentrated sulfuric acid is added to a hot solution of X. I mean, Na2B4O7.10H2O. You have plenty of water and you add an acid. What happens? You get boric acid, H3BO3. And boric acid is not highly soluble in water. It can crystallize out. Right? And what do you get? You get sodium sulfate and water. Is that all? Yes, that's it. Write equations. Let's balance them. You have 4 borons. I have 4. You have 2 sodiums. I have 2 sodiums. Sulfate. Well, I guess I would need only 1 sulfate in that case. Yes. And any water molecules? Let me check. I have 22 hydrogens. I have 12 here. So I can rather survive with 10 more. This is the balanced equation, my dear. BF3 reacts with lithium hydride. Yes. And if lithium hydride is in excess, I get LiBH4 plus LiF. This is what is obtained, my dear. Lithium borohydride. That is possible. Could there be a possibility that we have smaller quantity of lithium hydride? Yes. If you have only lesser quantity, then you can get B2H6 plus LiF. There are 2 possibilities like this. Sorry, BF3, right? 2 times boron and 6 times this will be, yeah. These are the balanced equations, and please don't forget, they are related also. Let me just clean this up, yeah. This is BF3. B2H6, if you react it with excess lithium hydride, if this was little, this excess, again B2H6 itself can be absorbed by lithium hydride to give you LiBH4. So these are all interrelated reactions. Can diborane react with water? Explosively. It gives you boric acid, H3BO3, and plenty of hydrogen, 6 hydrogens. Oh my God, yeah, this is the way it is, not 3. I'm sorry, in balancing it should be 6H2. Right? Right. NaH reacts with diborane B2H6. Well, what does it give you? It gives you NaBH4. Sodium borohydride, very popular reducing agent. On boric acid, when it is heated, you get HBO2 metaboric acid. If you heat it more, this is around 140 degrees Celsius to 180 degrees Celsius, yeah, and you get H2B4O7, which is pyroboric acid. And if you heat it to 540 degrees Celsius or more, you get a glassy substance B2O3. These are the products which you obtain on heating boric acid. Aluminium reacting with Na, which is such a favorite. Well, you get NaAlOH whole 4 plus hydrogen. This is the reaction. And if you want, you can always write this as NaAlO2 plus 2H2O. They are always in equilibrium with each other. Can we write down more things? Yes, it has, I believe, some water molecules. How many? Let's just balance and see. This is 3 by 2 H2, right? How many oxygens? 4 oxygens. We have 1 here, we have 3 here. I guess this does the job. The balancing is for the upper reaction and this is a different reaction. This is how you should consider this. Diborane plus ammonia, again a very striking reaction. You get what we say as BH3NH3 complex like this. You get an adduct, addition product or an adduct like this. Give one method for industrial preparation and one for laboratory preparation of CO and CO2 each. Well, not very difficult. See, first of all, lab preparation of CO and CO2. Lab preparation can be expensive. It can be done in test tubes. It should be easy to do. You take formic acid, and if you dehydrate formic acid using any dehydrating agent like concentrated H2SO4, it removes water and you get CO like this. This is one way of obtaining carbon monoxide in lab. Another method is you take HCOO Na and you just heat it. You find you are left with NaOH and it gives away CO. Both are, any of them, both are laboratory methods for obtaining carbon monoxide. What about carbon dioxide? Carbon dioxide can be very easily liberated. The easiest method is you take sodium bicarbonate and you add dilute HCl. You get NaCl plus H2O and great many bubbles of CO2. That is the best and the easiest lab preparation for carbon dioxide. You can also obtain carbon dioxide by heating carbonates, but this is way easier and far better. Then when you talk about industrial preparation of carbon monoxide, you could actually use water gas. What is water gas? When steam, superheated steam, is passed over red hot coals, you find it gives CO and H2. Wow, we have got carbon monoxide there? Yes, we have got carbon monoxide there. This is one of the very popular methods by which, my dears, carbon monoxide is produced. Look at this in a more typed and neatly written form. Same drama with some boundary line informations like temperatures. About carbon dioxide, even industrial preparation is much easier. How do you do this? Just heat limestone. There is plenty of calcium carbonate on earth, and if this calcium carbonate is heated to 900 degrees Celsius, it decomposes in calcium oxide and CO2, and that, my dears, is one of the very major sources of industrial carbon dioxide in case it is required. An aqueous solution of borax is neutral, amphoteric, basic, acidic. Borax is basic. An aqueous solution of borax is very much basic. B for borax, B for basic. Boric acid is polymeric due to molecules of boric acid undergo intermolecular hydrogen bonding and they form very beautifully planar structures. So yes, it is polymeric due to presence of hydrogen bonds. B is the answer. The type of hybridization of boron in diborane is, now diborane is BHH, H, like this, and one more H. So although these may be half bonds or whatever, 1, 2, 3, 4, there are 4 orbitals involved, there are 4 connections, and the hybridization is on an average sp3. Yes, it is sp3. Thermodynamically, the most stable form of carbon is graphite. Graphite is the most stable thermodynamic form of crystalline carbon. Elements of group 14A exhibit oxidation state of +4 only. Some of them exhibit oxidation state of +2 and +4, many of them. Form M2- and M+4 ions. No, not really. Form, because -2 anions, no, you get -4 like silicon 4-, but you don't get silicon -2. That is outrageous. This is bad. Forms M2+ and M4 plus ions. Actually, exhibiting oxidation states of +2 and +4 is much better. Carbon, for example, will not form carbon 4 plus cations. That is ridiculous and preposterous. But yes, it can exhibit oxidation states of +2 and +4. And please note, the word only is not there. What does that mean? That they can also exhibit other oxidation states, which they very well do. If the starting material for manufacture of silicones is RSiCl3, write the structure of the product formed. What exactly are silicones? Silicones are organosilicon polymers which contain repeated SiO-Si linkages. What? Silicones are organosilicon polymers. The keyword is organosilicon polymers, and they contain repeated SiO-Si linkages, and they have very extraordinary properties. Properties are not asked. Let's concentrate on manufacture of silicones. We are starting with RSiCl3. Fine. What happens? This RSiCl3 you hydrolyze, you add water. You get RSiOH, OH, OH like this, right? And if you get OH groups because of hydrolysis, do you know what happens? Yes, what? Actually, there is condensation reaction between adjacent silicon atoms. What do you mean? I'll just show you this. I'll need more space. I'll just erase this and write it. You have RSiOH, OH, OH plus HOSiOH, ROH plus HOSiOH, ROH. Fine. And then you have OH, Si, R. What stupidity is this? It is not stupidity. We are trying to write down a polymerization reaction as it occurs. And this is what we are trying to show, that what exactly happens in that respect. See, I'm just writing a sample. It is much more vivid actually. What happens is, you have this H and OH, they condense. What does it mean? This water molecule is removed, okay, in the same fashion. This water molecule is removed, and in the same fashion, this also continues ... and this also continues ... What about this? Again, a water molecule is being removed. Fancy. And again, a water molecule is removed. What are you up to? I'm just showing you how they behave. An OH group attached to a silicon atom is not very stable. Now, oxygens don't form double bond with silicon, so adjacent molecules begin to condense with each other. Wonderful. And they start eliminating water molecules. They do start eliminating water molecules like this. And it becomes very fashionable, you know, like this. It seems to get a kind of a ladder like this, okay? And where does that leave you? If we condense this, you know what we get? We get R, Si, OSi, OSi. You have R groups here, and you have OSi, 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 OSi. You get a ladder-like structure. This is ended. But on this side, it's a double-chained ladder which continues. And this is the structure of product, my dears, which is formed as a linear silicon. In fact, not linear, it's a cross-linked silicone. So dear students, this was the solution of NCERT questions of boron and carbon family. I hope you have benefited from them. If you want the theory, not just that, more deeper explanations, deeper ideas and more questions, you're welcome to visit Vyas app. The Vyas Edification app, the link has been given below. Download the app and access our content to your heart's content. This is Shishir Mittal from Vyas Edification. All the best.